Okay, today's lesson is on series circuits. Time to get serious, people. Yesterday we did a simple human circuit with one light bulb. Today we're going to look at a series circuit where there's two light bulbs, and tomorrow we'll look at a parallel circuit with the two light bulbs. The main characteristics of a series circuit is that there's only one pathway for the charge to follow. There's no forks in the road. For example, if we had a circuit like this, up at the top we have the battery, and then the positive charge, the fictitious positive charge that is, leaves the positive terminal, goes through here, and as it goes around there's only one pathway. No choice. You just keep going forward. Now you don't have to write this next bit down, but just to give you an example of where we're going next, tomorrow's lesson is on parallel circuits. We ready to go to the next slide? And with a parallel circuit, don't get paranoid. With a parallel circuit, as the conventional positive charge flow leaves the battery, goes through the wire, gets to this point here called the junction. Now there's a little fork in the road, and some of the positive charge flows up this way, and some of the positive charge goes down that way, and then the charge is reunited, and then all of the charge goes back to the battery. So that's tomorrow's lesson, parallel circuits. Today's lesson is on series circuits. Was there a question? Comment? Yesterday we talked about a 4-volt battery, which was 4 joules per coulomb, which was 4 blueberries per student. Now, if you have a series circuit, basically that coulomb of charge leaves with the 4 blueberries, and it's got to make its way all the way around with only those 4 blueberries, with only those 4 joules of energy. So, can that coulomb use all 4 of its joules, all 4 of its blueberries as it goes through that first light bulb? It can't use all 4 because then it wouldn't have any to get through the next light bulb. So what ends up happening is it uses up some of its energy to go through this one here, and then it uses up the rest of it to go through there. Since it's using some of its energy to go through the first light bulb, and then it uses the rest of its energy to go through the next light bulb, what would be the deal with these 2 light bulbs wired in series? Paulie? They would be dimmer. They're not going to be as bright. You know, they're only going to be using up 2 joules for every coulomb that goes through. Or 2 blueberries are going to be chomped down. So they're not going to be using as much energy per second, so they're going to have a lower power wattage rating, and they won't be as bright. So that's what I want to show you with my little demonstration here right now. Basically, I have this board, and with this board there are light bulbs. This overhead view, and then there's like these little connecting wires to the light bulbs. And basically, the way I have it wired is there's a wire that goes here to there, and then a wire that goes there to there, and then a wire that goes there to there, and then a wire that goes there to there, like that. Yes? And then I have my good old extension cord, which I, cut the ends off, the other end off. So here comes the extension cord, and then basically with the other end, there's two loose wires which are bare to go like that. And basically, you could think of this as being like the positive terminal of a battery and the negative terminal of a battery. Later on, we're going to see it's a little bit more complicated than that, but for now, you could just think of this as being like the positive terminal of a battery and the negative terminal of the battery. And what I'm going to do is, I'm going to connect that to various spots. So for example, if I connect that wire to there, and I connect the other one to, let's say, right there. Remember how you have to have a closed loop? Yes? Well, basically, the electrons, or I'm sorry, the positive charge flow would go through here, through this light bulb, to the negative terminal, and this light right here is going to light up. Woo! Yes? Now I know what you're saying, what about the other way? Why wouldn't some of the charge go like this? Hey, how you doing? Go through here, light up that bulb there, and then light up that bulb there, and then light up that bulb there. Because those four over there on the left, they're not going to go on with that first attachment. Why don't those four over there go on?
Are they attracted to the negative on the right?
What's that?
Are they attracted to the negative on the right?
They're attracted to the negative. As the charge goes over here, it's all attracted to that negative right there. Exactly. And is this part over here, is that part of a closed loop?
No.
No, that's like a dead-end road. So there's like nowhere for the charge to go. So basically, none of those light up over there. So let's take a look at this. Now, if I go back to this here, this time I'm going to take my plug and basically it has the the two wires, the positive and the negative right there, and I'm going to connect the the negative right to here and the positive right to here, like that. Yes. So basically, the positive charge flow is going to go through here, come around and go through there, but it's going to have to share all the energy, okay? So basically, this is a 120 volt source, yes, which means hands out 120 joules per coulomb, so basically 120 blueberries per student. And when that blueberry leaves here, it's going to have to use some to get through here, and then some to get through here. So these guys will light up. But what's going to be the deal with those two? They're going to be dimmer. So every time we add another bulb in series, it gets dimmer and dimmer. If we go over here and change this, and now I connect it over on this side, then the charge flow would go through the one light bulb, through another light bulb, through another light bulb, and this time they are just so dim. So now that we have like the basics about a series circuit, how there's one pathway, it's time to learn all the hidden rules that go along with series circuits. So let's draw a circuit over here. Da, 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 da. And up on top you have the battery. And this time I have 3 light bulbs in series. I'm serious, people. I have 3 of them in series. Now, whether I draw it like this, or if I draw it like this, those 2 are the same circuit. It's like artistic design, however you want to draw it. You know, those 2 are both the same thing. So basically I'm just going to stick with the one on the left, but you know, I could have drawn it this way. It's all the same. So basically I take that away. And the total EMF, the total energy handout, okay, I could label VT. And VT stands for like the total voltage, the voltage of the EMF. Sometimes it's referred to as the terminal voltage across the battery. And then some of that energy per charge is used to go through this light bulb. Some of that energy is used to go through this light bulb, and some of it is used to go through this light bulb over here. Those 3 resistances do not have to necessarily be equal to each other. So let's say that like this here is a bigger resistance than this one over here. Well, then this light bulb here would probably require more of the energy. So V1, V2 may or may not be equal to each other, depending on whether the resistances are equal to each other. However, we still can write down the hidden rule for the overall relationship between the total energy handout per charge, the VT, and the energy consumptions per charge, V1, V2, and V3. Can anyone read your physics teacher's mind and tell me what's the hidden law between those voltages? Okay. You guys don't see it? If yesterday, if this was a 4 blueberry battery, let's make it a 12 blueberry battery, yes? And then some of the blueberries have to be used here, and then some of the blueberries are used here, and then some of the blueberries here, because you always come home empty-handed. You always come home empty-handed. V1, V2, and V3 do not have to be equal. You know, if you came over here, good courage for speaking out. If you came over here and you got 12 blueberries, and you had to go through the 3 of them, and you always come back over here empty-handed. What has to be the deal with the 3 little guys compared to the big handout? They add up to it, exactly. VT equals V1 plus V2 plus V3. And I could say plus dot dot dot, you know, because if there was more in series, you know, I would just keep on adding up all the little guys. This over here is called the voltage source. It's like the source of energy per charge. And these guys over here are called the voltage drops. This one over here I always think of as like the energy handout. And over here, this is like the the energy consumptions. And we'll take our 2 o'clock stretch at this time. Okay. So we have our first series circuit formula. The total voltage source is equal to the sum of the voltage drops. Now, let's talk current. The electric current is the charge per second, the rate of charge flow. And we kind of like saw this yesterday with our simple circuit. If I call the total current leaving the battery I sub t, the total current I sub t. That's it. That's it. I sub t. Okay. And then the current going through this first light bulb, if I call that current I1, and then if I call this current going through the second light bulb I2. No, there's nothing there.
I1, it 2.
And then the current going through this third light bulb, I3. We sort of established this yesterday. If you have one closed loop, what's the deal with the current going through that closed loop? What's the current comparison at different points of the loop? David? They're all the same. Dun-dun-dun-dun. Only the names have changed. Yes. So basically, ladies and gentlemen, these currents are the same. IT is equal to I1 is equal to I2 is equal to I3 is equal to ... If there was more of them in series, they would all be equal to each other. The current stays the same. So that's our second heating rule for series circuits. I'm serious, people. Now, what about electrical resistance, opposition? If the opposition to go through this light bulb is R1, and then the opposition to go through this light bulb is R2, and then the opposition to go through this light bulb is R3, what would be considered the relationship between those three resistances and the total resistance of the circuit, RT? Keep in mind, ladies and gentlemen, the resistance in the wire is so small compared to the light bulb that we consider those, the wire resistance to be negligible. So the main resistance is through this light bulb, through this light bulb, and then through that light bulb. If you want to get the total opposition, the total resistance, and you got to go through R1, and then go through R2, and then go through R3, guess what the relationship is between all those suckers? See it, say it loud, say it proud. Put your hands in the air. Give me a stare. Come on.
They add up to RT?
That's what I'm talking about. They add up to RT. The total resistance is just equal to R1 plus R2 plus R3 plus however many more of them you had. You just add up all the little baby resistances to get the total resistance. So that's our third hidden rule. And finally, for series circuits, we can also apply Ohm's law to each device. Recall Ohm's law. The current going through a device is equal to the voltage across it divided by the resistance of the device. The bigger the voltage, the bigger the current. However, the bigger the resistance, the smaller the current. That's the way I like to present it, I equals V over R. However, the more popular version of this formula is V equals I times R. Vrr, vrr. I always think of like a German Shepherd. You know. Vrr. V equals IR. But the thing to remember, you can't mix and match the different variables. So if you're dealing with the total voltage and the total current and the total resistance, it turns out that VT equals equals IT times RT. Or if you're dealing with V1 and R1 and I1, it turns out that V1 equals I1 times R1. Likewise, V2 equals I2 times R2. And V3 equals I3 times R3. The biggest mistake that students make is they mismatch the terms. You have to be consistent. TTT or 111 or 222 or 333. The biggest mistake is doing something like this, saying the total voltage is equal to the I2 times, R1. You can't just mismatch. It's got to be consistent. This is a big no-no. So, ladies and gentlemen, here we have all of the hidden relationships that you need to solve series circuits. So let's try one, shall we? Okay, let's get to it. All right. Let's say we have a 12-volt battery, yes? And let's say that R1 is equal to 1 ohm, and let's say R2 is equal to 2 ohms. And what we want to establish is, what is the total current leaving the battery? How much current is going through R1? How much current is going through R2? What's the voltage across R1? And what's the voltage across R2? Now, the biggest mistake is this right here. Watch. Oh, I know Ohm's law. V equals IR. So, I see the voltage is 12 volts. And, over here, for this guy right here, the resistance is 2 ohms. Oh, so that's 2 ohms. So, I'm going to solve for I. Oh, I is 6 amps. What's the problem with that, people? Which voltage did I use there? That was the total voltage, but what resistance did I use? That was R2, yes? And you can't mismatch that. So that's a big no-no. What you really have to do in this problem first is figure out the total resistance. What would the total resistance of this circuit be? now that we know the total resistance is 3 ohms, anytime you have a device and you have 2 out of 3 for Ohm's law, VI and R, that shouts out, ooh, I got 2 out of the 3 for that particular device. So we could go right now and use Ohm's law for the totals. So basically, the total voltage is equal to the total current times the total resistance. What was the total voltage? 12 volts. What's the total current? That's what we're trying to find right now. And now we just figured out the total resistance is 3 ohms. So what does the total current come out to be? That's it. 4 amps. That's it. Once we know the total current is 4 amps, how much current is going through the other little guys, Paulie? 4 amps. Because what's the relationship between the currents? They're all the same. Only the names have changed. They're all 4 amps. So we know that these here are 4 amps, and this here is 4 amps. And then once again, once you have a device where you have 2 out of the 3, what does that shout out to do? Ohm's law. Vrr. Vrr. Whoopsie. V1 equals I1 times R1. V1 equals I1. What's I1? 4 amps. And what's R1? 1 ohm. So what's V1 going to be? 4 volts. Okay. And then what about V2 equals I2 times R2? So V2 equals I2, which is what? 4 amps, times R2, which is 2 ohms. So what does V2 come out to be? 8 volts. So this over here is 4 volts. This over here is 8 volts. Now we don't have to, but what's a little check we could do just to see that everything jived? What's a little something we just kind of notice, and we're like, oh, that's good, because that's the way it should work out. Add what up? The voltages. Look, it was a 12-volt handout, yes? 12 blueberries per student. And then 4 of them were used here, and then 8 were used here. And 8 plus 4 should add up to 12, and voila, it does. So, there you have it, ladies and gentlemen. The hidden rules for series circuits. The total voltage equals all the little baby voltages added up. The total current is equal to all the other currents going through. The total resistance equals all the baby resistances added up. And then Ohm's law can be applied to each device. You're going to learn to love these problems. They're like little Sunday crossword puzzles where you're given this piece and you're given that piece, and it's just using those hidden rules right there. So, enjoy. Okay?